Hello and welcome to Scholar Fedu. This is our UTME prep series where we provide relatively detailed solutions and explanations to the UTME questions. And in this recording, we're looking at the UTME questions for physics for the year 2011. This is the second and the concluding part of the recording. We are going to be looking at the next 25 questions in this in that year. Alright, before we continue, please don't forget to subscribe to our YouTube channel, like and share our content. You can also visit our website at scholar.com to practice the same exam for free. Next, on electromagnetism, which of the following electromagnetic waves has the highest frequency? Alright, the waves that make the waves in the electromagnetic spectrum, they are summarized as Riemann-Vox G. This is in order of increasing frequency, that is from the one with the lowest to the one with the highest frequency. And if you look at this order, alright, you see that from the options that we have here, X-ray here has the highest frequency. Alright, higher than X-ray is gamma rays, but we don't have gamma rays in this option here. So from the options that we have, X-rays here has the highest frequency, is of the highest frequency. Next, on light, when a red rose flower is observed in blue light, what color does the observer see? Magenta. Okay, the resulting color for mixing red and blue light is magenta. Next, on light, an eclipse of the sun occurs when eclipse of the sun occurs when light from the sun is not reaching the earth very well. Okay, when light from the sun is not reaching the earth very well, and this happens when the moon is between the sun and the earth, when the moon is obstructing light that is coming from the sun to the earth. That's when eclipse of the sun occur. Next, on sound wave, a cannon is fired from town X. How long is a sound heard at a town Y that is 4.95 kilometers away? We have the velocity of sound in air to be 330 meters per second. Alright, the distance here, the distance between the towns X and Y is 4,950 meters. We are given the question as 4.95 kilometers, so we convert that to meter by multiplying this by 1000. When we are converting from kilometer to meter, we multiply by 1000, so this will give us 4,950 meters. The speed of sound in air is equal to 330 meters per second. Now, why did we have to convert this to meter? Because the speed here is given in meter per second. So we cannot use kilometer and meter together. The unit has to be balanced. It has to be the same thing. So hence we converted this to meter. We then say speed. The formula for speed is equal to distance over time. But in this case, we are looking for this for time. So we make time the subject of the formula. Okay, by cross multiplication, time will be equal to distance over speed. Okay, time will be equal to distance over speed. So the distance, we have that as 4,950. Divide that by 330. That is the speed. We have 15 seconds. Next, also on optics, an image in a convex lens is upright and magnified 3 times. If the focal length of the lens is 15 centimeters, what is the object distance? Alright, magnification, the formula for magnification is equal to the image distance over the object distance. Now in this question, they said the image is magnified 3 times. That means that the magnification of the image is 3. Okay, so we are going to have 3 to be equal to image distance over object distance. To make V the subject here, we can cross multiply here. We will cross multiply this U here. So you have V to be equal to 3U. So that is that. Okay, you will also recall that we have another formula for magnification, and that is that magnification for a convex mirror is equal to V over F plus 1, where V is the image distance, F is the focal length, plus 1. Okay, so we have magnification from the question as 3. Alright, magnified 3 times, so the magnification is 3 equal to, now this V here, we are going to replace it with 3U. That was why we made V the subject of the formula here. We are going to replace it with 3U. Why? Because in this question they give us the focal length and we are looking for U. Okay, replace this with 3U over F is equal to 1. Then we bring 1 to this side here, so you have 3 minus 1 is equal to 3u over 15. 3 minus 1, that is 2, equals 3u over 15. Then we can cross multiply this 15 here. Okay, so when you cross multiply 15, you're going to have 2 times 15 is equal to 3u. 2 times 15 is 30, so you have 30 is equal to 3u. Then we divide both sides by 3, u will be equal to 10 centimeter. That is the object distance, 10 centimeter. Next, the capacitance of a parallel plate capacitor is 20 microfarad in air and 60 microfarad in presence of the dielectric. What is the dielectric constant? That will be equal to ratio of the capacitance in the presence of that dielectric over the capacitance in air. So that will be 60 over 20, and that is 3.0. Next, on electricity, if the charge of electricity per kilowatt hour is 4 naira, what is the cost of operating an electrical appliance rated 2.50 volts, 2 ampere for 6 hours? Alright, so here we need to calculate the electrical energy that is consumed by that appliance. Okay, and the electrical energy Q is equal to PT, the power times time. The electrical power here is going to be equal to IV, that is the current times the voltage of that appliance times the time. Alright, now here we have from the question, the voltage is what we have here, 2.50 volts. We have the current as 2 ampere and the time as 6 hours. So if you substitute all of that into this, current 2 times 2.5 times the time 6, we'll be getting 30 watts. We will then convert this 30 watts to kilowatts. This is 30 watt hour. 30 watt hour. We will convert it to kilowatt hour. That can be done by dividing this by 1000. To convert from watt hour to kilowatt hour, we divide by 1000. So if you divide this by 1000, we'll be getting a 0.03 kilowatt hour. Now in the question they said the charge of electricity per kilowatt hour is 4 naira. That means that 1 kilowatt hour is 4 naira. 1 kilowatt hour is 4 naira. So a 0.03 kilowatt hour is going to be equal to 0.03 times 1 kilowatt, which will be 0.03 times the cost of 1 kilowatt, which is 4 naira, and that will be 0.12 naira. That's 12 kobo, basically 0.12 naira. Next, we have a diagram here. We have to calculate the current flowing in the 12 ohm resistor. In this 12 ohm resistor. Now, when resistors are connected in parallel, the same voltage will be flowing through them, but different currents. Okay. Now, what we are going to do here is, since this is the same voltage that is flowing through them, we will then recall from Ohm's law that V is equal to IR. V is equal to IR. The V here is the voltage flowing through. Now in this case we are looking at this 12 ohm resistor. We are narrowing this down to this 12 ohm resistor. So the V here is the voltage through this 12 ohm resistor, which is the same for all of these resistors here. That will be 12 volts, equal to the resistance R, which is 12 ohms, times the current I, that is the current I flowing through this 12 ohm resistor. So you have 12 to be equal to 1 time I times 12 is 12I. Divide both sides by 12 and I will be equal to 1.0 ampere. Next, on work, energy and power, an object of mass 2 kg moves with a velocity of 10 meters per second round a circle of radius 4 meter. Calculate the centripetal force on the object. The centripetal force on the object is given as mv squared over r, where m is the mass of the object, v is the velocity with which the object moves, okay, in that circle, and the r is the radius of the circle. So you have the mass m, which is 2, times the velocity is 10, but we have v squared here, so this is going to be 10 squared divided by 4. 10 raised to power 2 is 100. 2 times 100, that will be 200. 200 divided by 4 will give us 50 Newton. Next, on electrostatic, the correct expression for the potential at a point distance r from a charge q in a electric field is, alright, so the electric potential capital V is given as K. Okay, this is the constant of proportionality from Coulomb's law times the charge Q over R. This constant of proportionality K is given as 1 over 4 pi epsilon naught. If you substitute that here, then I'm going to have 1 over 4 pi epsilon naught times q over r. So we'll be having q over 4 pi epsilon naught r. So we have q over 4 pi epsilon naught r. No squares. Okay, no squares. No square on the q and the r. Just q over 4 pi epsilon naught r. Next, also on electricity, 3 similar cells of EMF 2 volts and internal resistance 2 ohms are connected in parallel. The total EMF and total internal resistance are respectively. Alright, so to get the total resistance for parallel connection, alright, let's say we have 3 resistors that are connected in parallel. 3 resistors R1, R2, R3, and their effective resistance is represented as R. Then we are going to have 1 over that R equal to 1 over R1 plus 1 over R2 plus 1 over R3. So that's what we have here. 1 over R is equal to 1 over R1, that will be 2, plus 1 over R2, 2, plus 1 over R3, 3. Because there are 3 cells that has internal resistance each of 2 ohms. That means that our R1, R2, and R3 are 2 ohms. So this is the same thing as saying 3 times 1 over 2. So we'll be getting 3 over 2. To get the value of RT here, we are going to invert both sides. Okay, we will invert both sides of the equation. We will turn it over. That is 1 over RT will become RT over 1, which is RT. 3 over 2 will also become 2 over 3. Right? Whatever you do to one side of the equation, we do to the other side. 2 over 3 in decimal is 0.67, which is approximately 0.4. So the total resistance, total internal resistance is going to be 0.7 rather, 0.7 ohms. While now, because this is a parallel resistance, they are going to have the same, they will say the same PDF or EMF. That is 2 volts. In ohms, electrical appliances and lamps are connected in parallel because this is what parallel connection uses the lowest, okay, the lowest possible resistance and the lowest voltage. Okay, the lowest possible resistance and the lowest voltage. Next, 2 resistors 5 ohms and 10 ohms are arranged first in series and later in parallel to a 24 volt source. The ratio of total power dissipated in the series and parallel arrangements respectively is. Alright, so first we are going to find the total resistance in series. Okay, the total resistance in series. And how do we get that? That is by simply adding the resistances of the resistors here. So you have 5 plus 10, and that is 15 ohms. Then we find the total resistance in parallel, and that is going to like 1 over R is equal to 1 over R1 plus 1 over R2. So let's take this as R1 and this as R2. Okay, so you have 1 over 5 plus 1 over 10. Then we take the LCM of 5 and 10, which is 10. We then say 5 in 10, okay, that is 2 times 1, 2, plus 10 in 10, that is 1 times 1, and we have 1 here. 2 plus 1 is 3, so we have 3 over 10. Alright, to get the value of RP, we are going to invert both sides of the equation. We turn it over. So 1 over RP becomes RP, and this becomes 10 over 3. Okay, we turn this over 2, so we have 10 over 3 ohms. So this is the total resistance in series, and this total resistance in parallel. We will then use the formula for power. Okay, we say the power is equal to IV, and that IV is equal to V squared over R. Okay, V squared over R. Then we say V squared is equal to, if you cross multiply this R here, you have V squared is equal to PR. Now the voltage, okay, is constant here. Alright, the voltage is constant here. So you are going to say, I mean, the same voltage is supplied to both connection in series and both connection in parallel. So in that case, we simply say that the power, okay, the power in series times the ratio of the power, I mean the effective resistance in series, is equal to the power in parallel times the ratio of the times the resistance in parallel. Excuse me. Alright, then we can cross multiply. You can cross multiply. If you cross multiply, that means you bring this RP here and bring this RS to this side here. So you now have the ratio of the power in series to the power in parallel to be equal to the ratio of the effective resistance in parallel to the effective resistance in series. Alright, the effective resistance in parallel, we've calculated that here as 10 over 3. We then say this is divided by the resistance in series, which is calculated here as 15. So we are going to have 10 over 3 divided by 15, which will then become 10 over 3 times 1 over 15. Then we have 5 here is 2 and 5 here is 3. So you're going to have 2 times 1 2 over 3 times 5, and that will be 15. So the ratio of the power distributed in series and parallel is 2:15. Next, two balls X and Y weighing 5 gram and 50 kilogram respectively were thrown up vertically at the same time with a velocity of 10 meters per second. How will their position be 1 second later? Alright, we will say that both of them, they will be at the same time. They will be at the same position. They will be at the same position. Alright, why? Because it is the same. They are moving with the same velocity. The velocity is the time rate of change of displacement. Now if they move with the same velocity under the same unit time, then they should cover the same distance. Okay, they should cover the same distance. So we just go with this option. X and Y will both be 500 meter from the point of throw. That is, they will move the same distance. That's basically what that is what this that's what is communicated in this option. Okay, that basically, forget the value here. Okay, the point is they will be same distance from wherever they are starting. Okay, from the point of throw, as the case is here. So both of them will be the same distance. They will move the same distance since they are moving with the same velocity. Next, which of the following will be applied when a metal Y is used to electroplate another metal X in electrolysis? Alright, so in electroplating basically is a process in which one metal is used to coat another. Alright, and there are many reasons to that. It could be for aesthetic, for design purpose, or it could be because there is a quality that we desire in that metal that it does not have. Okay, so we want to kind of like introduce it in it. So we find another metal that has that quality, and we use it to electroplate and all of that. Now in electroplating, the metal that you want to plate, that you want to electroplate, is going to be made with a cathode. Okay, now we want to use this metal Y to electroplate metal X. Okay, it is metal X that I want to use to electroplate. So this X is going to be the cathode, while Y is going to be the anode. Okay, X will be the cathode, Y is going to be the anode, and we are going to use an I current. Okay, we are going to use an I current. So Y is going to be the anode. Okay, and a very high current is used. Next question. A radioactive isotope has a decay constant of 10 raised to power minus 5 per second. Calculate its half-life. Alright, the formula for half-life is given as in 2, which is 0.693 over the decay constant. So you say this is equal to 0.693 divided by 10 raised to power minus 5. Now if you want this 10 raised to power, this whatever you have here, to come to the numerator, this is the denominator of the fraction. Now this is 0.693 over 10 raised to power minus 5. If you want this to come to the numerator, okay, then this sign here is going to change. Okay, this sign here is going to change. So this is minus 5 here, it will become plus 5. We are now going to have 0.693 times 10 raised to power 5. Now I want to put this in a standard form. How do we do that? Is we will rewrite this is 0.693 as 6.93 times 10 raised to power minus 1. I am shifting this point to this place here. So I will say this is 6.93 times 10 raised to power minus. I am using minus here because this is a number less than 1. Okay, it is a number less than 1. If you express number less than 1 in standard form, you are going to have a negative power. So you have 6.93 times 10 raised to power minus 1 times 10 raised to power 5. We can now use our law of indices on these two here. If I have 10 raised to power x times 10 raised to power y, that will be equal to 10 raised to power x plus y. So 10 raised to power minus 1 times 10 raised to power 5 will be 10 raised to power minus 1 plus 5, and that will be 10 raised to power 4. So you have 6.93 times 10 raised to power 4 seconds. Next, on magnets, which of the following is a property of steel? Steel is used to make permanent magnets. Okay, it's used to make permanent magnets, where it can retain its magnetism for a longer time. Next, on photoelectricity, if the threshold frequency of tungsten is 1.3 times 10 raised to power 15 Hz, what is its work function? We are given the Planck's constant here as 6.6 times 10 raised to the power minus 34. Alright, work function omega naught is equal to hf naught, where this h is the Planck's constant and f naught is the threshold frequency. So this is going to be the Planck's constant, which we are given here as 6.6 times 10 raised to the power minus 34, times the frequency of that tungsten, which is 1.3 times 10 raised to the power 15. You then say 6.6 times 1.3, that is 8.58, times, we now use our law of indices on this, 10 raised to the power minus 34 times 10 raised to the power 15. This will become 10 raised to the power minus 34 plus 15. So you have 8.58 times 10 raised to the power minus 9 joules. Next, on AC theory, in an AC circuit, the ratio of RMS value to peak value of current is, alright, the RMS value of the current is given as the peak value I naught over root 2. Okay, if I want to now get the ratio of RMS value to peak value, that will mean I over I naught. So how do I get I over I naught from here? I'll just cross multiply this I naught here. If I bring this I naught here now, I'm going to have I over I naught, that is the ratio of the RMS value to the peak value, to be equal to, once I have removed this I naught here, I'm going to be left with 1 here. Okay, I'll be left with 1 here, so I have 1 over root 2. So the ratio of the RMS value to peak value is 1 over root 2. Next, two inductors of inductances 4 Henry and 8 Henry are arranged in series, and a current of 10 ampere is passed through them. What is the energy stored in them, that is in the inductors? Alright, first we are going to calculate the total inductance. Okay, the total inductance LT, and that is obtained here because this is for series connection. We simply add this up. Okay, 4.8, so that will be 12 Henry. That's total inductance. We then see that the energy stored in the inductors E is equal to half times I squared, that's the current passed through the inductors, times the total inductance. So you have this to be equal to half times I, which is 10 here, the current is 10 ampere, so you have 10 raised to the power 2 times 12. 10 raised to the power 2 is 100. 1 over 2 times 100 is going to be 50 times 12, which is 600. Okay, so that is the direct solution here. However, we don't have this here, so we are going to assume that the inductors were in parallel. Now if they are in parallel, instead of adding this together like this, okay, where we've gotten this 12 ohms, then we'll do 1 over the total inductance is equal to 1 over, say, L1 plus 1 over L2. We take this as L1, we take this as L2. We then find the LCM here of 4 and 8, which is 8. 4 in 8 is 2 times 1, 2, plus 8 in 8, 1 times 1, that is 1. 2 plus 1 is 3 over 8. So we have 1 over LT is equal to 3 over 8. To get the value of LT here, we are going to invert this fraction here. That is 1 over LT is going to become LT over 1, which is LT. If that happens here, the same thing must happen to here. So this 3 over 8 is going to become 8 over 3. We then go back to use this formula for energy. Okay, so we have half times the current square, that's 10 raised to the power 2, times the total inductance, which in this case we've calculated, assuming that the inductors were connected in parallel, we've calculated that to be 8 over 3. So you just use 8 over 3 here. Alright, and by the time we calculate all of this 10 raised to the power 2 is 100. 1 over 2 times 100 is 50. 50 times 8 divided by 3 will give us 133, approximately 133 joules. So we'll go with that option there. Next, on matter, under which of the following conditions do gases conduct electricity? So gases can serve as an electrolyte. They can conduct electricity under low pressure, okay, under low pressure and high potential difference, under very low pressure and high potential difference or voltage. Next question in AC theory. In measuring high frequency alternating current, the instrument used is the Hot wire ammeter is used to measure high frequency alternating current or direct current. Next, the bond between silicon and germanium is, that's a covalent bond. Okay, it's a covalent bond. the silicon and the germanium, they form a covalent bond. Okay, which of the following materials has an increase in resistance with temperature? Those are ohmic conductors, and that is metals. Okay, metals generally, their conductivity, their electrical conductivity, it reduces with what? With temperature, and their resistance increases with temperature. Alright, finally, the electrical properties of germanium can be altered drastically by the addition of impurities. The process is referred to as. Now, germanium is a semiconductor. The addition of impurities to a semiconductor, okay, usually to increase its conductivity, is regarded as doping. Okay, that is termed as doping. The addition of impurities to a semiconductor to increase its conductivity is doping.